Okay, so today I want you to do the exact opposite of what we did last class meeting, and that is I want you to consider this function, and I'd like for you to go ahead and graph it on a sheet of paper. The function that we're considering is y equals 3x squared, and I want you to do what we call evaluate it from x equals 0 to x equals 4. And you'll recall we learned last year that the derivative is basically a way of talking about the instantaneous slope, or the slope function of whatever the function is you're looking at. And in this case, we also learned last year that the opposite of that, or the other function, when you take the area bound by the curve, is what we call the integral. And so that's what we're discovering today, is we're looking at what an integral is. And so I want you to go ahead and graph these points and do kind of a best fit curve as best you can. And then let's think about how we could evaluate or look at the area bound by this curve. Well, one thing we could do, since we've got a piece of graph paper here, is we could count up the squares. That's what you did last year in AP1, right? You counted squares, and we would need to figure out the dimensions of one of these squares, and of course it's 5 up and 0.2 to the right for a total of 1. And then because I told you that we're going to look at it from x equals 0 to x equals 4, we shade in this green region, and that's what we're trying to find the area of. And so I could go through and count up the squares, and I get 50 whole squares, and then if I look at kind of what's beyond those whole squares, there's some part ones, and so it would probably range somewhere between 50 and 60 as the area. And that's not awful, but we ask ourselves, is that the most exact thing? Because if you look at all these partial squares, I mean, exactly what part is that? And I just kind of clumped them together and made a pretty rough estimate. And so a better way to do it might be to kind of break this curve up into rectangles. And so I could look at these orange rectangles, and notice that this far right orange rectangle is about the equivalent to 32 high and 1 wide, and then the one between 2 and 3 is about 15 high on average, and of course 7 and 3 for a total of 58. And so that sounds like that might be a little more precise than our approximation just counting the whole squares. But what would be better? Well, what if we broke it down into even smaller rectangles? And now the width is 1/2, but I get heights of 40, 25, 18, 13, 10, 8, 4, and 2 approximately. And when I add up those areas, I get to 60. And so it looks almost like, kind of like we saw with our differential one the other day, it looks like it's almost converging towards something, right? It was 50-ish, and then it went up to 58, and now it's 60. And I could do this 1 or 2 more times and make the rectangles even smaller. And like we said with the derivative, we're looking at the concept of a limit, and as the width of those columns approaches 0, then the total areas that I'm adding up are going to approach the total area bound by the curve. And so again, that's exactly what we're doing in calculus when we take the integral. And so I want you to think about it for a second. We talked about how to determine what the derivative was, and I've just told you, as you learned last year, that slope and derivative are kind of the opposite functions of area bound by the curve and the integral. And so if that's the case, if integrating this thing is kind of the opposite of differentiating or taking the derivative of it, then you might look at the function and say, y equals 3x squared. What function would it result in 3x squared when I took its derivative. And of course, doing a little bit of figuring, you can anticipate that the function that when I took the derivative by the power rule that you learned, that would give 3x squared would be what? Y equals x cubed, right? In other words, if y equals x cubed, then if I take the derivative of y with respect to x, then I get the function 3x squared. And so if 3x squared is the derivative of x to the third with respect to x, then x to the third would be the integral of 3x squared with respect to x. And so what does that mean? Well, it means if we take that function x to the third and we evaluate it at our limits, which in this case I told you was from 0 to 4, we evaluate it at 4, and 4 cubed is 64, and we evaluate it at 0, which is 0, and we take the difference between those two. And when we take the difference between those two, we get the value of 64. And like I said, right, you can see that that was kind of approaching that limit. It went from 50 to 60-ish, 58, 60. Again, if we made the rectangles even smaller, guess what they're going to eventually converge on? That is 64. And so again, this is kind of a picture of what's happening with an integral, just like we did with the derivative. And so what I'd like for you to do now on your own is do what I just did with this one for the following functions. I want you to graph and evaluate a function y equals 4x, but I want you to consider the boundaries from 3 to 6. And I want you to do it both ways. I want you to actually calculate the area, which of course this one's going to be linear, and so that's going to be easy to calculate the area, but then I also want you to prove it by finding out, hey, what is the function that is the integral with respect to x of 4x? And so do it both ways, both graphically, proving it with the area and the power rule for integrals. And then I'd like for you to do the exact same thing for this function. I want you to take y equals 2x plus 2 and evaluate it from x equals 1 to x equals 5. All right.